This video is going to talk about belief propagation, or more accurately, it's going to be a very brief sampling and a rough introduction of belief propagation. And the reason I say that is because there's a huge amount of knowledge and research that's come out in the past, let's say, 30 years or so, maybe 40 years now, about belief propagation, and more specifically about inference in undirected graphical models that we will not be covering in these videos and can fill an entire, graduate education. But hopefully I can give you some of the basics in this video, at least enough to see how it relates to inference in Bayesian nets and things like the forward-backward algorithm. So the video will be structured like this. So I'll start by briefly reviewing Markov random fields, at least just to refresh your memory from the last video. Then I'll show you the algorithm. I'll show you sum product belief propagation, which is one of the most important variants of belief propagation, which allows us to compute marginal probabilities given the full joint factorization. And then I'll show you how we do belief propagation in trees, and then I'll show you how that generalizes the inference algorithms we've been using for HMMs. And somewhere in there, I'll throw in a discussion about loopy belief propagation, and I'll mention at the end some of the other ideas, research ideas that are interesting topics in this space. So to review Markov random fields from the last slides, the last video, an MRF is a graphical model that describes the independent structure of a joint probability distribution, and specifically it identifies a factorization of the probability distribution into a bunch of potential functions along the cliques of the graph. So in this case, and throughout this video, we're mostly going to be thinking about situations where the cliques are edges. And things get a little bit trickier when we go to the fully general form, which I've shown on the slides here, where we're dealing with cliques of arbitrary structure. But for now, we're going to consider edge-based cliques. So all the factors in our factorized probability distribution will have two variables each. So if we think about inference in this type of factorized distribution, it should look kind of similar to things we've done so far. So this is the probability distribution. And if we're interested in finding the marginal probability of any particular variable in the set of all variables in X, we might write something like this, right? So this is the probability of some variable X subscript S equaling some state, lowercase x. And we compute that by summing over all of the possible states of the entire X vector such that XS equals X little xs. So this is the same principle we've been working with in other distributions where we specifically sum out all the variables not involved in the marginal probability we care about. So to be more concrete, some of this notation can be really hard to read or even write down succinctly because we're dealing with unordered vectors of random variables and trying to index into them, and some of it gets a little bit clunky. So let's be more concrete. So let's look at this Markov random field. This was the one from the previous example. And we might be interested in finding the probability that variable A has some particular state. And we would do something like this. We would sum over all of the values, all the possible values for B, C, D, and E. Here I'm using a shorthand also for, again, because the notation can get clunky. The long form, or the shorthand form, is that I'm writing phi of A comma B to mean that the phi of the random variable capital A equals little a, and the random variable capital B equals little b. So of course this is really expensive to do if we just compute it the way it's written out, right? Because if you have n variables, and k states, then you have to sum over k to the n minus 1 different states and evaluate the function for those different states. So we would hope that there's a way to compute this faster, and there is a way to do it for certain structured MRFs. So this is something called sum product belief propagation, and it's one of many variants of algorithms that are called belief propagation. And the specific variant, or the sum product variant, is used to compute marginal probabilities. But the basic foundation to these belief propagation algorithms is that they pass messages between variables. And the messages for sum product belief propagation have this form. And and the idea is this is a formula for computing a message from S to T, some variable S to some variable T. And the messages themselves are functions of the variable that is receiving the message, right? So it takes this message here takes xt as input, and then the idea is once you compute all the messages between all of the adjacent variables, all the variables who are neighbors in the graph, you compute beliefs, which represent the estimated marginal probabilities of each individual variable by just multiplying together all of the incoming messages. So in both of these expressions, the function neighbors takes a node in as input and outputs all of the nodes in the graph that are adjacent to that node. And then on the messages update, it's important to note that the product inside the sum, which is also why it's called the sum product algorithm, the product inside the sum excludes the variable that is receiving the message. Right? So you're always sending a message between two adjacent variables, and in order to compute the message, you have to sum over a bunch of things, but each of the things inside the summation has to collect messages from all adjacent nodes of the sender variable, except for the one that's receiving the message. Okay, and that's super confusing. So let me draw some pictures. So let's look at how we compute the message for node B to send to node D. Right, so if B has to send a message to D, then what we do is we are going to collect messages from B's neighbors, and specifically we're going to collect messages from A and C in this image. So A and C send messages to B, and we use those to compute the product inside the summation, and then we and then we pass that to variable D. And that's a little bit weird, but the math ends up working out if you have the patience to work through the equations. But I think the intuition or the analogy is that if these messages are bits of information being passed around by the variables, then the intuition is that you don't want if D is receiving a message from B, you don't want D to receive its own message to B in return, right? So what B is basically telling D is, here's all the information that I can get from my neighbors about your probability, but I'm leaving out the message that you're sending me right now. And then the other part of the computation is computing the beliefs. And when you compute the beliefs, you do include all of your neighbors, right? Because there's no receiving message. It's just computing your beliefs for your current variable. So in the case where we want to compute the beliefs for node B or for variable B, we would include all of its neighbors, A, C, and D. And I've highlighted here in yellow the general equations, and then everything else was just working out the examples for this particular graph. So a few notes about these messages. You can think of them as functions of the receiving node's variable, right? So remember, if we go back, the equation of the message, or the definition of the message, always takes in xt as an input. So it's a function of xt, and it's the message received by xt. So it's always a function of the receiving node's variable. And in discrete variable space, right? If these x's are discrete variables, then these are easily thought of as vectors, in the sense that it would be a function of discrete inputs. So you can just treat the different possible states of the discrete input as the indices in a vector. And just like we worked out in the math for the BayesNet message passing, you can and should normalize these messages in practice, because they can get really small because there's a lot of products in their computation. And lastly, I wanted to mention that there's an alternate form, one that, for example, you often see in textbooks like the Kevin Murphy book, that explicitly encodes the unary and edge potentials. And the form of all the equations then looks like these. I'm just listing them. You can pause and stare at them for a while if you want. But I think the key difference is that there are now these unary potentials that just take in one variable, right? So there's a phi sub s of x of s, just takes in one variable, and this is just a further factorization, but the number of parameters in this form is strictly more than in the other form, because you have unary potentials in addition to the edge potentials, or in addition to the clique potentials. And what's sort of unfortunate about that is that you could have easily just absorbed the unary potentials into the edge potentials. Or you can just take that function, multiply it in, and just treat it as if it's part of the edge potential. And that's the form I showed you, is the more compact form. But occasionally, for modeling purposes, it may be more useful to represent this unary and this form with a separate unary potential. And then one thing to note, I guess, is the beliefs now include the unary potential when you compute them, but so do the messages. So it's kind of interesting how all that works out. Okay, so I've given you this general form of message update equation in this, or rather, I've given you two forms with the unary potentials and the one with only the clique potentials. But what I've described to you so far essentially implies one type of message passing, generally called loopy belief propagation. But that's not the only way you can do this. And if you have an MRF graph structure that looks something like this, where it's a tree, right? There's no cycles in this graph. Then you could run loopy belief propagation. It would work fine. So that's where you iteratively update each message and just keep updating all the messages one at a time. Or it's also equivalent to think of it as updating all of them in parallel. Right, that's loopy belief propagation, and it is guaranteed to converge to the correct marginals, which is good, but it's also wasteful, because there's another way to run message passing on tree structure graphs that is much faster. So this is called the collect and distribute schedule, or there's a few names for it, but I call it the collect and distribute schedule. And the idea is you start by computing messages that collect all the messages to a root, or you collect all the evidence from leaves to the root. So you start from you pick one node as the root. In this case, I picked the gray node as a root, and you find all the leaves of the graph, and you compute the messages to their parents. Now of course, this is an undirected graph, so there aren't really parents. But if we choose one node as the root, then we can compute which are the figurative parents in this undirected graph, right? Because the figurative parents here are the nodes that are one step away from the leaf, that on the path toward the root. So we compute the messages toward the root, and then we continue until we collect all the messages at the root. And one side note is that if the graph is a tree, because it's undirected, any node can be a root technically. So it actually doesn't, well, it doesn't exactly matter which one you pick as the root for this procedure. So once you've collected all the messages, or all the messages toward the root, you can now do the second phase, which is to distribute back to the leaves. So you can think of what's happening here as you collect all the evidence, and now the root has gotten messages from nodes that have seen other nodes' information, and essentially incorporates all of the information in the graph. And again, the math works out here, but the analogy is easier to think about. And the analogy is that when you collect data, or when you collect messages, when you do this, it's analogous to some sort of hierarchical information collection. So the parents of the leaves have collected information from the leaves, and then their parents collect information from them, and then until all the way goes up to the root, and the root's neighbors have all of their information about their subtrees, and then finally the root has all the information about the graph. Okay, and then at that point, once you've collected that information as the root, you can then pass down all that information to all of your descendants. So you send messages out from the root to all of its neighbors, and then you send messages from those neighbors to the next neighbors all the way to the leaves. So this is the collect and distribute procedure, and it's guaranteed to converge to the marginals, but just like loopy belief propagation. But the nice thing is that it just takes one update per message. So remember, there's one message for each direction on each edge. So there's 2 messages per edge, and in this collect and distribute procedure, we traverse each edge once to collect and then once to distribute. So we actually only update each message exactly once, which is a linear time operation, which is really great news for tree structured Markov random fields. Now, the guarantees are not as nice in non-trees, and for, let's say, I don't know, about 10 years or so, it was a popular technique, right? People started using it because they said, well, this works well in trees, and let's just try it on a loopy graph and see what happens. And they found that it worked really well in practice most of the time. But for most structures, you can find adversarial cases where it does something really bad. So as a rule of thumb, you can treat loopy belief propagation as approximate inference. And there have been certain structures that have been identified in research where this is not the case, where it's actually a guaranteed approximation or it's actually the guaranteed exact inference. But in the worldview where we think of Markov random fields as these general purpose models where we can go in and change the structure if we want to as modelers, then in that case, it's the best thing we can do is hope that we can get a good approximation with loopy belief propagation. Okay, so with that, I wanted to point out that what I showed you just now with this collect and distribute procedure is pretty much the same thing that we've already seen in something else. So in an HMM, we have this structure, and let's say we convert it from a Bayes net to a Markov random field, like I showed you in the last video. Now, if we let the rightmost hidden state be the root of a tree, we could do collect and distribute, where we collect messages from these leaves, and collect in this fashion, fusing together information from the observations with the estimated beliefs for the hidden state. So this should look kind of familiar, and then we can go and do distribute, which looks like this. And maybe we would also distribute to the leaves if there's some unknowns there, but most of the time we'd observe those, so we wouldn't necessarily pass messages to variables we've already observed. But right, as you can probably guess, this is exactly the forward-backward algorithm. And as with other things in this video, if you have the patience to go through the math, you'll see that these are actually equivalent after you do the conversion from a Bayes net to a Markov random field, and then once you do belief propagation, you'll see that you're computing the same updates as forward-backward. So that's good news that this algorithm that takes a different view of factorized probability distributions does essentially the same thing and has the same nice properties as the Bayes net forward-backward algorithm. Okay, so to summarize, belief propagation passes messages between neighboring nodes, and the idea is that it fuses all the incoming messages from all neighbors except for the receiving node, right? And then it sends that the message to the receiving node. And you can do things like collecting evidence and distributing, which is a serial order in trees, which leads to exact marginals in trees. Or you can iterate in loopy graphs, or in trees actually, which leads to approximate marginals. And when you iterate, it's usually done in parallel. Although there are some interesting research contributions where people figured out other schedules that were not based on collecting and distributing in a tree, but had ways of updating the messages in loopy graphs, in cyclic graphs that have maybe nicer behavior in certain settings. So that's the basics here. But there's a ton of research on these things, both the Bayes nets and the Markov random fields that I showed you in the past few videos, that we won't be able to get to in this class. So I wanted to leave you with one thought that I think is one of the most interesting aspects of belief propagation in Markov random fields, which is that the messages are related to Lagrange multipliers for enforcing consistency constraints on estimated marginals. What that means is that when we think about the marginal probabilities that we're trying to compute with belief propagation, or some product belief propagation, we know that not all numbers between 0 and 1 form valid marginal probabilities. And if we write out the requirements for any set of marginal estimates to be truly from a consistent joint probability distribution, we end up with a bunch of linear constraints. And in fact, we end up with an exponential number of them. But because of the factorization, sometimes we can simplify those, or sometimes we just simplify them anyway. And we end up with a bunch of simple equality constraints along the factors of the Markov random field. So if we then try to enforce those constraints with Lagrange multipliers, and at the same time try to optimize an objective function that has something to do with the entropy of the estimated distribution, there's a lot of details I don't want to get into here, then we end up with the message passing belief propagation update rules. So this is a fascinating connection that has led to a lot of really interesting research in the past few years, I guess going on about 1.5 decades now. So of course we won't be able to get into that too much in this class, but I wanted to give you a little preview of it before we end this segment.